recording now, right?
Yeah, yeah.
Yeah. So you can, okay. So like everybody can download DS9 from the download page. So you just Google DS9. The first thing finally comes up is DS9, and not the Star Trek Deep Space Nine, which actually has a very interesting history, because the earlier version was called NGT, that is the next generation, and then according to Star Trek, the next thing is DS9, that is Deep Space Nine. So that's why it was called DS9. So you can download it from here. It supports various different distros. It supports Linux, it supports Windows, it supports Mac OS. Very simple to install. Just download it, pip install it, or just for Windows it's just you just download the file and it just open it. In Linux it's slightly more complicated. You have to use the you can use the command line. Just type DS9. If it's installed properly in your machine, it will open up DS9, which it should do now. So this is DS9. So it's a GUI based thing. Everything is like very comfortable. You have files, edit, view. So everything is self-explanatory as well. There's a help desk, there's a reference manual, there's a user manual. There's also a story about DS9. So there's a lot of things that you can do. So let's open some FITS files. So I have made a folder on my desktop. So I'll just go navigate to the desktop, and the folder is called DS9 tutorials. So let me open a FITS file. So as I was saying, that FITS files are the way the astronomers typically communicate their data. So let me open this FITS file, and huh. So this is the FITS file for this is the so this is a pan-star image. This is an optical image in the Y band. So this is about zero point 0.8 microns or something. I don't remember what exactly pan-star Y band corresponds to. So you see that there are a few stars, 1, 2, 3, 4, 5, 6 stars. Um, but what I can do is, if I click on, if I have my mouse in Linux, what I can do is I can left click on my mouse and drag it. So that will change. You see this slider on the bottom, right? So this is,
Mayank, can you hear me?
yeah, I can hear you.
Yeah, yeah. So Saurav has a question. He
Huh.
says how to do it for Mac. I don't understand which version is applicable.
So Mac will have so it depends on what Mac distro you have, right? If it's a big, if it's 11, then download it for the 11. If it's you're using some older version like Sierra, then 10.3. So this, I think, Mac
I
versions.
have I have 11, but there are two options for 11. I think
Uh, I'm not
X11 big.
see like so there would be some to avoid warning about unknown development. Please, so try. I have never tried it with the Mac, so you can just give it a shot and see which one works for you. Try both, or there will be just Google it and see. Right, there will be some answer on how to install it on Mac.
So I see two options now. One is Aqua Big Sur, another is X11 Big Sur.
Uh-huh.
So whichever is applicable for your.
His Yeah, his distro or something. I think one would be with the X11 terminal, and one would be with an Aqua. I don't know whether there's an Aqua terminal or not, because X11 is typically a terminal which is associated with Linux and Windows. So I don't know what's the equivalent on Mac. So just Google. I'm certain there would be a answer to this question, like which one we have to use, because a lot of people are using Mac OS as well. So just Google it and see. I'm not an expert in Mac, so I can't give you a definite answer. For example, if it's Linux, um, I will say use Ubuntu 18 or 20 or Cent OS if you're using Cent or Debian, or one of these can do.
Can we use this Ubuntu 20 for Ubuntu 21?
I think so. That should work. In principle, that should work. Or you can always do it through the source. You have the source. You just compile it for your machine. So that is also one option. So just try and see what works for your machine. So like installation is, I'm certain there will be uh some what do you call, so there's a help page as well. So you just, so this also maintains all the windows and all source codes, everything is there. So just see which one works for you guys. Okay. Install, like if it's a Linux machine, or Windows machine, I can help with the installation. Mac, I'm not an expert, so you can try. uh, so yeah, so let's get back to this. So this is a FITS file. So uh, like one way of changing, so let's say this is the default contrast is something like this. So one way of changing the contrast, so that is that these black things get that these white things get highlighted, is if you right click on your mouse and drag it across the screen. So you see this this bar, this black bar at the bottom, that gets shifted. So you can shift how much of it is white, you can shift this. So this is basically representing counts, and you can change it, change the counts, or you can do this. You can go up and down, so that will change the color scale, like how black this gets. So this is like something that you might have to do manually to see what brings out the best image. So from your for your perspective, so you can basically right click and just drag it around on in both X and Y direction, so that way you can change the contrast, make it look prettier. But sometimes what can happen is that there is a lot of information. So right now what we are seeing is just these bright central stars, but I know that there is a lot more nebulosity or a lot more fainter objects in this what do you call data set. So what I can do is I can click on scale. So there is a scale option here. I can do a log scale. So you see suddenly the scaling has changed. Now it's a log scale. So now it goes from 10 to power 2 to 10 to power 6. If I do linear, it goes from 10 to power 5 to 10 to power 6. So log scale definitely has changed the way it gets scaled. So now you start seeing that a lot of, so for example, this particular star, this was not there previously, right? So if I do a linear scale, you only see, even with best, you only see this star. But if I do a log scale, you'll easily see this smaller star, this fainter star has come up. You also see this nebulosity here, which is also now much more easily highlighted. So with the DS9, you can use so there are various different options. Like you can use a power law. So this is a power law index. You can use a square root kind of a function, which is good if you have, again, then you can use a squared function. You can use a sign or a sin h. So these are all various different methods of doing this. So let's say I want a log scale, and then there are also different ways of let's say you want to select a range of data, right? So you want to select data from a particular range to a particular range. So you can use a z scale, for example. So this will be the like very high something. So this will uh, give you a much more blown up thing. You can use min max. This will give you something different. You can also do scaling from here. Like you only want to include data up to 99%. So you can do this. You can include 90% of the data. So this is everything gets blown up. You can do user defined scale. You can do a lot. You can do z scale. So a lot of these things you can do. So let's just go to min max and log scale. So this is the first thing that you can do with DS9, so that you can open up a FITS file and practically see what kind of stars, like now you know what kind of field you have. You can see the different number of stars that you have. So you can zoom in, like let's say if you have a huge FITS file, you can zoom in. This is a small enough FITS file that there is no point in zooming in. So let me open a big FITS file. So if you have it properly installed in your machine, what you can do is you can actually just directly open the FITS file through DS9. Let me see if there's the DS9 tutorial. DS9 tutorial. So here I have, let's say, files from uh, the Orion star forming region. So these are Spitzer images. So these are basically huge files. So in the previous one, everything was coming in the field of view when I opened that file. So let me also open that file as well. This was this one. So you see this file, it's centered at the thing. I can zoom in, zoom out. But if I open the other file, this Orion file, so you see that it's a very huge FITS file. So I can basically use the scroll wheel to scroll in, scroll out. I can do a zoom fit. So this will fit the entire file onto the window. I can then zoom in 1/4, 2/4 once. So I can also change the scale. So let me go to a log scale. So in the linear scale, you don't see much. You just see some bright point sources. But I can do a log scale and you start seeing the tendrils of the Orion Nebula. I can actually zoom in a lot, so you can start seeing tiny stars. So these are the stars. So so if you look at this corner, can you see this top right corner? So this basically, this cyan box tells you what is the field of view that you are seeing. So you see this field of view. So if you zoom in, this field of view gets smaller and smaller, but you can still see that this is a lovely image because you can still see the point sources. So, and this is just and here this is just a zoomed in version of that. So say you don't want this to look black and white, you want, so but this is a single image right now. So this is a single channel image at 4 microns, but let's say you don't like it black and white, you want it some other garish color. So you can highlight, you can change the contrast and see what you want. So what you can do is, for example, if you're not interested in, let's say, the inner structures, what you can do, if you're only interested in the outer structures, you can change the fits file contrast to make sure that you can see the tendrils and all. But you can change the colors, but these are not real colors, these are just some scaling colors. So typically a lot of people like it red, so it gives you an anonymous field. So heat, so this is also very typically favored bow. But you can see that you can get some you can basically change the color scale and get a lot more information. um, so now let's see, so now let me just get it to default gray because I like it that way, and also log scale. Okay. So now let's see what else can we do from DS9. So we have seen how to open a fits file. Now let's see,
I have a question.
Yeah.
When a scaling is done, suppose a logarithm or power or square root, it just takes the pixel value and does the logarithm on that pixel value, right?
No, it divides the pixels into a log scale. Like if you have, it does an internal calculation. So if you have data ranging from one milligents, one count to, let's say, 10,000 counts.
Okay.
So it will try to divide so for example, it will try to divide the range into a log scale. So 1 to 1 to 3, 3 to 10, 10 to 30, 30 to 100. So it will try to have a logarithmic kind of scale for the contrast ratio. So it's not like it's taking a log of the points, it's just taking a logarithmic, it's just showing colors in a logarithmic interval. So it will become much clearer if we have discrete colors. Let me see if I can get a discrete one with discrete color. So here it's a discrete colors. Okay. So if I do, let's say, a scale of linear, so you see this is 9 into 10 to the power 4, 1.8, 2.7. So basically it's 9 into 10 to the power 4. So it's adding. Okay. So now if I do a log scale, so now that interval has changed. Now it's not the same. It's not the same interval, but it would be equally spaced in log scale. So that kind of things you can do.
Okay.
So basically, for example, we have a star. The intensity of it is like surpassing the things around it. So we take the log scale, and
it's somewhat linear. It somewhat takes it to a scale which is more
which is
appropriate.
visible in front of the star as well.
Yeah, but it's also somewhat arbitrary. Like, for example, I like this, but you might say that, okay, I want it slightly more like this or something like this. So it's also somewhat arbitrary how you define it. So it's up to your preference that how, like, let's say if I'm only interested in the brightest stars, so I'm fine with this kind of a scaling as well. But if I'm only interested in like very bright cores, then this kind of thing. But let's say if I'm interested only in the outer envelope kind of structure, then I can have a scaling which will basically wash out inner details, and I'll just have the outer details. So those kind of things are somewhat user specific, so that you can see. Scales, colors, zoom we have done. So sometimes what can happen is that it's more so when you don't have, let's say, let's get into then the other thing. So this can also give you coordinates. So if you look on the left hand side top panel, you see certain things written. So file, it tells you what the file is. Then there is something called object. So that tells you what object, or basically what was the object that the fits file was made for. The next is the term called value. So it tells you what is the value of what is the count or flux or whatever units you're using for a particular pixels. For example, if I zoom in here, so this particular pixel has a value of 17,089. So a pixel outside only has about 400. So this tells you what's the value of the pixel. The next thing that you see is this FK5. So FK5 is nothing but the array deck of the object in J2000 coordinates. And it also tells you what is the physical coordinate. So basically this is an image of certain pixel by pixel. Maybe it's an image of let's say something like 7,800 across, and something like let's see something like 2,000. So it's 8,000 cost 2,000 kind of an image. So if you want to say what is the pixel number for a particular star, you can just put it there and it will tell you that this particular star which we are seeing. You can also see on the top right corner the zoomed in window for that star. So this particular star has a pixel value of 1964 and 3991. So those kind of things you can do with the DS. So you know the physical coordinates as well as the array deck coordinates. Let's say you want to see how this coordinate would look like in J1950. Maybe you're looking at an old paper. You want to match things with an old paper. You can do J2000. You can do JK4. So now everything is in 1950 coordinates. So it's like the array deck has changed, but the pixel coordinates will still remain the same. That is, the physical coordinates will still remain the same. Let's get back to the current era. You can also do galactic coordinates. So if you're interested in galactic latitude, longitude, so L and D, so you can do that as well. Again, the pixel coordinates will remain the same. Let's say sometimes you want array deck, because let's say you can do array deck as well. Let me go array deck in degrees. So now instead of R minute second, now it's in degrees. So you can also change these kind of things. So we have seen scaling, we have seen color, how to change color. Now we have seen also the physical coordinates. So FITS files carry a lot of information. One of the informations that they carry is in their header. So that can tell you who observed it, how it was observed. So what you can do is, or which telescope it was observed in. So you can click on files, you can go to header. So this will tell you all the information about that particular thing. So this FITS file originates from the Spitzer Science Center. The telescope name is Spitzer. The instrument is IRAC. You can also see what kind of an observation type it was. It was an IRAC map. You can see the field of view. You can see who observed it. So this was observed by Giovanni Fazio. So first name, last name. So you can also see what was the name of the proposal. So depending on who writes the FITS file, you can see a lot more information. Like typically you will have certain information, like what is the number of X pixels, Y pixel, that you will typically have. You may or may not have an observational date. So you also have when was this FITS file observed, what is the name of the object. So then there are like, what is the coordinate system? It's IRS in 2000 epoch. Then the coordinates are in array and deck. So all those information are available in the FITS header. It would also tell you what is the units of the data. For example, this is Megajansky's per steradian. What is the unit of the image? And in principle, it can also tell you how was the data reduced, like if some of the people, so processing history. So this tells you what pipeline was used, when it was used, how it was arrived at. So lots of things. And then you can always save this as a text file if you really want to. So, okay. So now let's see, I want to, so
I have a question, Mayank.
Yeah, Manshu.
What is the difference between FK5 and ICRS? Because whenever I search on SimBadge, I see FK4, but I don't see FK5. I see ICRS.
So ICRS, so there is a subtle difference. I don't remember exactly. So one is taking precision into account. One does not take precision into account. I think so. I have to see. I'm not 100% sure, but that you can look up. We can look up. So yeah.
Yeah, in the header file, each pixel must carry some. Each pixel must be equal to some array deck value, right? So which one says that?
So this is, I think this one, these things, CPR. So this is it's reference pixel. Then this gets referred to the reference pixel. So there's a reference array and reference deck. So all these things internally it does. So DS9 does a lot of things. like if you want to do it manually, you will go crazy. DS9 just opens any, just give it a image fits file, it will just open it without any questions. So we have seen the header file. So now let's say you have huge number of stars here. But let's say you want, so I know that this is Orion region and I know a few stars that I want to look into. So what I can do is I can do something like, there's something called analysis. So there's something called name resolution. So if I know a name of a star, let's say I know the name of the star is Hobbs 68, I can do retrieve. So it will get me the RA deck from Simbad for this particular star. Then what I can do is I can pan to it. I can then put a crosshair. So now this tells me that this particular star here is Hobbs 68. So Hobbs is a catalog of stars. So this tells me that this particular star is Hobbs 68. So that way you can quickly find the star that you're looking for in this data by doing a name resolution. What you can then do is you can say Simbad or Vizier or Ned, whatever query catalog you want, or name resolving service you want to use. Next, what you can do is, let's say now we have our star, right? Let's say I want to know what is the typical flux associated with the star. So what I can do is I can go to edit. So for name resolution, I can go to analysis and name resolution. So now let's say I want to get roughly a photometry, roughly what the amount of flux that is there in the star. What I can do is I can go on edit, click on region, and then click on then from edit, basically what edit does, it changes my cursor to maybe a crosshair, to maybe the color bar, or to maybe a region. So let's say I want to do region. I want to know what is the flux associated with this particular star here. So what I can do is I can go to select make my cursor into a region, go to regions. Let's say I want to select a circle because I want to do a photometry kind of thing. I do a circle, I click on circle, and I can just drag it over here and it will create a circle. So let's say I want to place it here. I can double click on the circle. It will give me the RA deck, the central coordinates in degree RA deck. So let's say let's say this is the RA deck for Hobbs 370. What I can do is I can call it Hobbs 68. I can select, let's say I want to have my circle, let's say in arcs, I can change the units to arc seconds. So I want a circle which is 5 arc seconds wide. So I can do this, apply. So now you see this has created a region, which is a circle called Hobbs 68. And you can see the name of the circle. What I can do is I can create multiple such regions. So let's say I call this some other name, Hobbs 69. So it will create another region called Hobbs 69. So let's say now I want to know what is the flux in this particular region. Okay, what is the number of counts? Since this is in this is Megajansky per stadium, I want to know what is the flux in this region. I can double click on this. So it will again give me this dialog box. So I can change the color of to green, yellow, whatever you want. I can change the line thickness to something, let's say 3. I can do analysis on this. So let's say I want to know the statistics. And the statistics I want to know is, so that will give me all the statistics of that particular row. What is the central RA deck? What is the total number of counts in that thing? The error associated with that count? What is the area of that circle? What is the typical surface brightness, which is sum by arc second square? Then what I can do is, what are the number of pixels which are lying in this circle? This is 51 pixels. What is the mean flux of these pixels? It's 903. Median, minimum, maximum, standard deviation, RMS, everything it gives. So typically, so this is the RMS. So you know that, so this is the RMS. So in principle now, what I can do is I know the sum. So I know that this is this many megajanskis per steradium. So I have the sum. What I can do is, so for example, this is, let's say 45,000. What I can do now is I can place my region with a similar circle. Let's say this is also, let's make it, this is also 5 arc seconds. So now I have placed it on a region of the sky where there is no star, no flux associated with this. Okay. So what I can do is I can also look at this, get statistics. So this tells me that for a 5 arc second circle, just the background contribution is 3, 4, 6, 6, 8. megajanskis. So if let's say 3500 megajan 35,000 megajanskis. So what I can do is 45,000 minus 35,000. So that tells me that my source has a flux of 10,000 megajanskis per steradian. So you can do a very basic photometry just by making apertures and just taking the sums and subtracting out the sums. So you can do a very basic photometry quickly with DS9. Does that make sense? Any questions till now? Okay, not. Then let's go to. So regions are a very powerful tool. Let's say now I have gotten the photometer, but I also want to see how does my typical star look like? What is the, let's say, telescope response, or how does my star look like? What I can do is I can click on shapes. I can do a line. I can drag a line across the, let me just delete this. And deletion is also easy. You just click on it and press delete. So I can do is region, shape, line, and I can run a line across this. So this has drawn a line across the star. I can click on the line. So it will tell me the length of the line in degrees, angle of the line, starting point, ending point, everything. I can do a 2D plot. So this then gives me a first order cut of the star. So this tells me that it's somewhat like a Gaussian, but again, since it's peaks at the center. So I know I can calculate something like from here I can calculate something like the FWHM, all those kind of things I can do. I can export this as a text file. I can smoothen it. I can do a lot more things with this. So this way you can do very basic telescope characterization with using DS9. Yeah, so this is all about regions and analysis. So any question till now? So we'll jump into something slightly more complicated or slightly more interesting as well. Any questions? So we have seen how to use regions. We have seen how to use. So what you can do is, so sometimes let's say you don't have, you get an image which does not have any physical coordinates. It's just the pixel coordinates. It might be that you are using a telescope. Let's say you are using our department telescope. So typically small telescopes don't give you an array deck automatically. So you have to associate an array deck with it in using IRAF. But let's say you know that the way, so this is how the image looks right now. There is this elongation around the XY around the Y direction. Let's say I want to rotate this. I can rotate it by 90 degrees. So this is how the Orion Nebula will look like on the sky. So it's along the plane of the sky. So this is how it would look like typically. I can invert X and Y axis. So it's now fifth. I can just invert the y-axis. I can just invert the x-axis. I can do all sorts of funny things with this. So let's say I can also crop. I can just crop it, saying that I want a center at this. I want something like this. So it will just crop my fits file. Let's say I want to crop it to 0.5 and 0.5 degrees. So it's a square region. So it has cropped my fits file into this square region now. And what I can do is I can do a zoom. So one of the problems with DS9 is whenever it saves a file, it saves the entire thing. So what you have to do in principle is like, for example, if I save the file right now like this, it will save the entire thing with this white background. So I have to do a zoom fit and then save. So I can go here. I can export it save it as a FITS file. I can save it as a TIFF file or PNG. Let's save it as a PNG. So this would then go into, again, so this is my home, Mayank Narang, desktop, DS9 tutorials. I'll call it ds9.png, save, okay. So now if I go to this folder, it has saved this ds9.png file. You see that since it was not, so since there was white background on either side, so it will take this white background as well. So this is one of the problems with DS9, that it will always do this kind of a annoying thing, that it will never save it as a perfect square. So it saves whatever it sees on the screen. So now let's exit. So now let's say you want to, so DS9 is very powerful. So right now what we saw was an Spitzer image from Iraq. You can do optical. This is an image from Pan-STAR. You can do 2 mass. You can do any kind of FITS files. So this is mid-infrared FITS file. So So this is a good point. So you see this FITS file. So what this FITS file has multiple channels in it. So this is channel 1. So by channel 1 I mean, so it stores, it's a multi-dimensional FITS file. So it's a multi-dimensional array. So it stores X, Y, Z, and then there is another axis, let's say X prime. So if you look at, so it's basically a multi-sliced, it's, I don't know, it's, you get what I'm trying to say, right? It's like there are multiple slices in this FITS file. So the
multi-cube, actually.
it's a multi-cube. So the first slice is basically the image data. So you see this, these stars. The second is the error associated with these images. The third is some crosshatch pattern. Fourth is also some crosshatch pattern. So the first is basically the real data, and rest of them are just the error associated with the data and other things. Yeah. So this, you can also open ALMA, like that is your, what do you call?
Mayank, can you open the last file again? And so from where you got this multi-cube option?
It automatically comes. You open it, it will automatically come if it's a multi-cube file. It's a cube. If it's a spectral cube, it will automatically come.
So it's if a FITS file have many extensions.
So
you can also go to file and open multi-cube. There is option.
You can go in frame and open multi-cubes. So frame has that option. So go to frame, cube, cube. So it will then give you this option.
Okay.
Okay. So yeah. So as I was saying, you can also open radio file.
When you said that it has multiple slices, does that mean for a particular XY pair, it has multiple Z values?
Yes.
All of the Z values represent
different things. For example, in this image, the first thing represented the flux. The second Z represented the error in the flux, and the last two don't really matter for us. So it can also, I'll show you another example where you can also store spectral information. So this is you can also open ALMA images. So this is an ALMA image of a protostar. So as Amrish was saying, this what other information can we have? So this is an ALMA cube. So this is again, it's a spectral cube with multiple Y columns. So you see now this is this is basically frequency. So this is the image XY, and the Z column represents frequency. So for each XY pair, we have an intensity, and for each XY intensity, we also have a frequency. So I can keep on changing this. I can play it as a movie. So it will go through everything. So like somewhere here, so you start, let me just change the scale as well. Thoda sa, Z scale, maybe linear only, linear. So you see this white dot here, right? This white elongated thing. So if I play the movie, so this will keep on changing. So this is basically CO emission. So it's a CO spectral cube. So, and so you can do all these kind of tests as well. So you can quickly go through and see whether you have a detection or not. If I go on the opposite side, you start seeing the blue shifted jet. So you start seeing a jet here now. So this is the blue shifted jet, and this is the red shifted jet on the other side. So these kind of things you can do with DS9. You can look at ALMA FITS cubes. To the first order, you can easily do it with DS9. So we have seen many things now. Let's say now what I want to do is I want to merge a few images. So let me see. What I can do is, let's say I want to create a colored image. Okay. So let me just open this. So these are, I'll show you an object. Anybody can anybody guess what this object is? So let me just do this. So do you guys know what this object is? Exactly. So this is, I think Himanshu, you're muted, but yeah, this is the Eagle. Himanshu is correct. This is the Eagle Nebula. So again, you see this is in the, so typically when you see this Eagle Nebula, it's always like towards the north south. So what I can do is I can do I can align the image. So this is the typical, this is now in physical coordinate. This is how NASA would look, this looks like. So these are narrowband images. So this is at 502 nanometers, which corresponds to either a sulfur line or an oxygen line, maybe a this is the sulfur line. So what I can do is in DS9, what you can do, you can create colored images. So what I can do is I can open file. So I can open frame and I can click on an RGB thing. So now I can create RGB frames. Let me see files. Okay. So now what we can do is create an RGB file. So open. So let me put the 673. This is an oxygen line here. So this is now in red. So you see how it looks in red. What I can then do is, where's my, so now what I can do is, let's go to green channel. I can open another FITS file here. Let me give, this is hydrogen. I have added a green channel. Let's say I also want to add a blue channel to this. I'll again go here, click on blue, open files and add a blue channel. So this is, now we have made an RGB. So from a black and white image, we have gone to an RGB colored image. We can change this to, let's say, again, this is more to do with what kind of, like, it's also some user preference. Let's say some people might like this way. Some people might like it slightly differently colored. So those things you can always mess around and change. So let's say I like this. This looks good to me. So this is a so from a single colored black and white image. So typically astronomical detectors, they will produce a black and white image. So from a single black and white image, which looked like, let me go here, look like this thing. We have gone to a colored image that looks like this. So we can also save this thing. Let's save this as a, let's save it as a PNG. And this will automatically save in desktop. Eagle Nebula, it will save. Let me just open this and so again, you saw that it saves only the, so right, the way I had zoomed in the photo, part of these edges were being clipped. So if you can see here, part of it was being clipped. So if I zoomed out, then it will save the entire image. So this is one problem with DS9, but you see we have made a colored image. So yeah, you can do this kind of things as well. Okay. So yeah.
Excuse me.
Yeah.
Sir, you mentioned sulfur and oxygen line. So that corresponds to the specifications of the detector, right? What does it mean?
So sulfur and oxygen. Okay. So you can do something called narrowband imaging. So there are spectral lines. So you can just observe in a very narrow window, like from example, 655 nanometers to 657 nanometers. You can just observe 2 nanometer wide band, and that will give you the oxygen. Like it will only look at emission in that base because of that oxygen line. The rest of the emission doesn't care about. So it's called a narrowband filter, as opposed to broadband filters, which have a much larger wavelength range. So narrowband is like you're just cutting off light from everything except maybe 2 or 3 microns, not microns, nanometers.
Okay.
So let's say I want to, I can do this. So you can do DS9 star fits. It will open all the fits file in a given folder. Like it will tile them nicely. So let me also scale them properly. Scale, log scale. So you can click on each of these and individually scale these. So this is now. So let's say I like this view. Okay. Now what I can do is let's say I select this image. I also rotate this so that it looks nicer and properly aligned. So align. So now what I can do is, so now let's say this is in one coordinate system, right? So what I can do is I can align all these images based on this image. I can go on frames, then go to match frames, world coordinate systems. So all the images now are aligned in the same pattern. So let's say if we want to look at how the flux changes from one wavelength to the other, so that might tell us that what is the dominant component. Let's say you want to do this kind of an analysis. You can go on frames. You can do blink.
So this time you have 3 different fits file for the 3 different bandwidth, right?
This, yeah. So so even the colored fits file that we made, that's basically these 3 fits files over plotted on each of them.
So yeah, okay.
So let's say what I want to do now is let's say I want to see how does the flux change from one filter to another, or how does my stars change from one filter to another. So what I can do is I can do blink. So there's an option in the frames called blink. So it will cycle through all the 3 fits files simultaneously. So I can say I can do also this for single. Sorry. Where is it? Frames single. So let's say you see this fits file. So this particular outer rim looks very bright here. I can go to the next one. So here it has slightly faded, and the other one also it looks bright. So you can do blinking, or you can do this manually. So and see how things change. So this, a lot of people in the asteroid community, when they're searching for asteroids, they use this. So they'll have the same patch of the sky being observed for several days. And if you have an asteroid, what will happen is that from frame to frame, that asteroid will, the position of that particular asteroid will change. So you can use blink to actually search for asteroids. So this is something that some people do, not us, but yeah, that is an option. That is also a very powerful tool in DS9. So we have seen how to make colored images. We have seen how to make, yeah, basically this is more or less like to the first order what you can do. DS9 can also be used to open spectra. Like if you know what you're looking for, you can open spectra as well with DS9. Let me just show you that. So this is spectra. So I won't recommend it for spectra because that it treats like a single pixel wide line, or a few pixel wide line. So what you can do is you can, let's say if you're in a hurry, you don't have IRAF installed, and Python might take forever to read the spectra, and you just want to see whether you have that line detection or not. You can go to region, select region. You can select a straight line, and you can just drag it from here to here, and just analysis, plot 2D. So this gives you to the first order how the spectra looks like. And this is very good because you can see some telluric lines here, some of the other lines here. So to the first order, this is a very powerful tool to do these kind of things. This is not, you can just not just look at the reduced final spectra, but this can also be used to analyze basic, let's say, like the raw spectra itself. No, this is not the raw spectra, tungsten lamp. Okay, tungsten lamp chalega. So this is a lamp spectra. Again, you can scale it, log scale. So you see some lines kind of things. So this is basically the response of the detector. You see this circle, right? This is the response of the detector. So you can do a lot of first order things with this kind of thing as well. So here is a proper astronomical spectra. So my target is somewhere here. It goes like this, and you can see some bright lines. So those kind of things also you can do with DS9. Yeah, so this is basically it. Do you have any other questions?
Yes, I have one question. In between, you were telling that if the telescope doesn't provide this celestial coordinate system in the image, then what to do?
You use IRAF then. IRAF mein karna padega. But unless like
if the image doesn't contain this celestial coordinate system in it, then how can we do that? Manually or somehow?
Yeah, you have to do it manually in IRAF, like adding celestial coordinates. It's what I was talking about is like if you have a small enough field of view that you just have 1 or 2 targets, you can just quickly.
No, it's a global cluster.
Then you have to do it properly by doing it manually by like adding it in IRAF and all. So like else what you can do, again, that would be difficult. So I can, like for example, this is the entire Orion region. What I can do is I can create an RGB file for this, but instead of using so what you can do is you can actually mix match telescopes with different resolutions as well. So let's create an RGB file. Let's look at red, and red, maybe let's open So let's go to something longward. Let's say we go with MIPS image. So this is at 24 microns, the same region, but at much longer wavelength. So what I can do now is I can then add a green thing. This will, I'm not doing it, I say time pass clear. This will show you something very important as well. Let's say I can add this channel in green. And then I'll add one more thing in blue. Open. So these are basically three different instruments with slightly different what do you call PSFs and all. So let me get this to look like this. Let me just select green. I can change the green scale to log. So now we have green also showing up properly. Blue also we do log scale. Log scale, so it looks nice. And then we add blue and green and then red. So so now if you look at here, so let me zoom in. So you can move the cursor with this. Let me see some right. So pan. Pan. So you see here, you see the star. There's a central white portion, and also there is a red halo around the star. You guys see this? You know? So yes. So this is happening because but do you see this is happening because both Spitzer and both IRAC and WO have very different MIPS and IRAC have very different resolution. So if I only do let's say apna IRAC 1 and 2, you see that there is some halo, but that halo is very diminished. But if I add the red one, you start seeing this halo is much brighter. That is because if you look at MIPS itself, you see that the spot size is much larger. But in principle, DS9 doesn't care about the spot size, so you can do this kind of things. I can also change this red image to, let's say, something else. Let's say I want to change it to another image, which is this one. Where is this one? First. Yeah. Did it change? Yes, first. It did. So, okay. Now let me go here. Red view. So you see that the red image is just this big. Let me just also change the scale. So this is the red band image. It's very tiny. It's just this patch. But again, with DS9, what you can do is it doesn't really care about the other thing. So you see, even uneven fits files you can put on one down. So this is the red coverage. So even uneven fits files you can put on top of one another. So now you can see clearly the so this is the IRAC. This is the PAX 70 micron image, and this can be overlaid, and you see this whole structure now. But outside, you see that this is just blue and green. So it's just this particular region, because this is where the data was. So you can see this data. So it becomes very powerful for quickly doing these back of the envelope things and matching things. Yeah, I think that should be enough for today. Any other questions, comments? We can always discuss these more.
Mayank, I had a question. I'm sorry if you have covered it before.
But no problem. Bol.
How do I get the FITS files? Where do I get it?
FITS files. So that depends on like that we haven't covered actually, but that depends on what you want to do. Let's say I want to look at something called 2-mass. So I can do 2-mass archive. So this will give me images from 1.23 microns to 2.6 microns. So I can go to 2-mass archive. I can do interactive image service. I can, let's say, give me a name of a star that you want to look at, or a globular cluster. We have 5 months. I'll come in like 5 minutes, 10 minutes. So yeah, so give me a name of a star, or I can use something.
M53. M53.
M50. M53. So that's a globular cluster, right? So let me, so this is the M53 globular cluster. So let's say I want to download iska J-band image. So just click on download. So this is the J-band image.
So every telescope's archive should have this data to be downloaded as of itself.
In principle, it should, but sometimes it doesn't. So
Okay.
this is your M55 cluster. So it's slightly off-centered, but depending on what wavelength you want to look at, you can do like this is the M53 cluster that you want. So let's say this is an infrared. Let's say you don't want infrared. You are like mere ko optical mein hi kaam karna hai. Then let's say there is something called ZTF archive. So that will give you optical images and hello.
Okay.
So again, let's do M30, 50, 55, 30, 53 now. So again, you can do resolve. So it will give you now an optical image of this cluster. So let's say this is the optical image. You can do prepare download. Prepare download. So download. Oh, ho gaya download. Yeah, sorry. So you click open this. It's taking time. But it has downloaded now the same data in optical now. So this is the same cluster now in optical. So does that answer your question? Like,
yes.
Yeah, you can always know there are multiple archives on with using different wavelengths that you can always get these data. Any other questions, comments, suggestions?
Can you just show some other archive?
There's ZTF, 2mass, Spitzer is there. So Spitzer. So again, depends on what you like. Spitzer archive is there, so that can give you again images and everything. This
how do you reproject the? How do you reproject data? I mean, suppose you make your own headers, and you have some other data, and you want to reproject that data on your new header. How do you do that?
That is complex. That you can do in Python. That is not a very easy task. I think Python has some routines to do it.
Yeah.
So like
I actually did it in Python, but I wanted to cross check.
So this will give me the Spitzer. Again, download this map. So this will give me a Spitzer map of this particular globular cluster. And okay. So this is a Spitzer map of that particular globular cluster. So different wavelengths may also you'll see different things. Different telescopes will also have different resolution. So let me then scale log. So now you're seeing very little stars because most of them might be not very IR bright or something. So those kind of things you can then look into with different telescopes. There's also Herschel is there, Galax is there, Pan-STAR is there. So and depending, ALMA is there, Weiss is there. So there are many data reduction archives, data archives available online. So it depends on your science case that what suits you.
Okay.
Anything else? If not, then we'll end today's session. Okay, then we'll end today's session. Thank you everybody. I'll see you.
Thank you.
Yeah. We'll see you around. Okay.